and L in any one of the different directions, either X, Y, or Z, you can get, but you can't get all three of them.
Right. So but what we did find, in fact, is L squared. And it can be any one of them, Lx, Ly, or Lz equals 0. And so that means we can find, so because they commute,
With certainty, you can find L squared and L in one direction with certainty, but the other two you get uncertainty.
I don't know, I don't like the word direction there. I mean, for me, a better word would be here. You can find an eigenfunction that contains the simultaneous values of L squared and L squared and Lz. Right? And what is that eigenfunction?
Shortage your equation?
Well, that's an equation. I asked for an eigenfunction. What's the eigenfunction that has the simultaneous values of L squared and Lx?
The rotational.
The solutions to the rotational, the angular part of Schrodinger's equation, yes. What are those solutions?
Spherical.
Spherical harmonics. All right? Yeah? All right. So what we found out last time, or what we talked about, is L squared on Y, L, ML. What does that equal? First of all, it's angular momentum squared. So what do the units over here have to be?
Angular momentum
Squared. So how about an h bar squared?
L plus 1,
L times L plus 1.
and then the split by
Okay.
Y.
And indeed, it's an eigenfunction, so that's y to the L and L. All right. At the same time, what is LZ acting on y to the L and L? What does that equal?
ML is H bar.
H bar ML y to the L and L. All right. So again, what are the spherical harmonics? I agree with you. They're the angular, the theta and phi, the azimuthal and the polar angle solutions to Schrodinger's equation when you do separation of variables for a potential that is just a function of
Space.
well, yes, just a function of space. It's not a function of time. And in particular, a potential in spherical coordinates is just a function of r. All right? So this is very powerful because almost all these problems that we're talking about, the potential is a function of r. All right?
Is it because, like, if it wasn't a function of r, you wouldn't get a spherical harmonics?
If it wasn't a function of r, you do separation of variables and you get a different answer. Okay? The reason that we were able to do it is that when it was a function of r, we were able to separate out. That's not weird. Separate out. Separate.
That's right.
We were able to separate. Doesn't that sound?
That's right.
We're able to separate.
I'm doing soft.
That's what I heard.
Yeah, that's what I was doing. I was jumping it off. By the way, Jeremy, I'm bringing you a car on Tuesday. So next Tuesday, we're having a department party, right after I finish.
Really,
What's the guitar going to
It will, but I'm going to attempt to play a little bit.
Let's play the music one thing for that.
Which always amounts to me not being able to play anything stuff. Which is Jeremy.
Maybe I'll bring it.
Okay. And I'd rather you play too, right? So rather you play.
I have an acoustic bass guitar. Much easier to hold it around.
Separated.
All right, well, let's get going. All right, so we've done you installed the
Separated.
Okay, but let's draw what this picture looks like, okay? All right? What this picture looks like. So this is X, Y, and Z.
So the eigenfunction that simultaneously shares both the eigenvalues is the spherical harmonic.
You said it in a way that I'm not particularly happy with.
All right.
It's an eigenfunction that simultaneously has eigenvalues
Produces.
of, it simultaneously has eigenvalues of L squared and LZ. all right? But let's paint what this picture looks like. All right, so H bar ML is what? What are we calling that? It's the
Projection of
projection of the angular momentum L onto what axis?
To the z-axis.
Z-axis. So over here, this height right here is H bar ML, from here to here. And if that's a projection, where do I put the total angular momentum?
In the xy plane.
Okay, well, yeah, a little bit like that, but it looks like this. This is L right here. All right, now, what is the magnitude? So this is the magnitude of L, and what is the magnitude of L equal to?
H bar square root of L plus 1.
H bar square root of L times L plus L. Okay, so this is the picture of angular momentum. All right, so you know when we always say like a p orbital has an angular momentum of L, what is the actual magnitude of angular momentum for L equals 1? So
H bar
Like,
the 2
square root of 1
times
times 2, so square root of 2. Yeah. So when we're talking about the p orbital, which has an angular momentum quantum number of 1, what is its actual magnitude?
H bar square root of 2.
You got the deal, okay? And then you can see that when this, and you can think of this as spinning around, right? This angular momentum is precessing around the z-axis.
Yeah.
Notice that for this magnitude, as it precesses, what is the projection on the z-axis always going to be? Does that ever change?
No.
No, but what does change is what's happening to, in this plane, you know, Lx and Ly, and that is always changing with time, all right? And you don't know that for certain. But what you do know for certain, and these are why they're the eigenvalues, is that for a given L, you have an ML projection. All right? So, let's do some calculations now. Let's do this. Let's do the expectation value of L squared. How am I going to calculate an expectation value of L squared?
Sandwich it in between the
Put
two
it back
side
into the
numbers.
eigen-
Okay, nope, I'm not doing that. I'm doing what Jeremy was saying.
Put in the sandwich of it. I mean, we don't want to write the whole integral out now, so just write
Right.
bracket.
So expectations are that sandwiching of the operator, right?
Yeah.
That's just what goes back to the basic ideas of probability, all right, that we talked about. But in general, it would look like this. It would look like on the bra of n prime, L prime, L, and L prime. And so this is the ket, the bra from the ket of a hydrogen-like orbital. And then in here, I would put L squared. And over here, I would put N, L, ML. And what is that going to equal? What?
1. Better
the
1.
Delta.
Oh, the chronic delta.
Okay, I want a delta,
L
All right.
prime, L prime.
and I also want something else too. This is going to operate on here,
So,
so what's it going to pull out?
L's and MLs.
Because remember, this is like R of R. What does this stuff stand for?
It's the
Y,
spherical harmonic.
Y to the
the
L, ML. So what
Pull
do we
out
get?
the-
Pull out the ML.
So pull out H bar squared L. with L
H
plus
bar
1.
squared, L times L plus 1. Now what? The delta function, and that's got to be of N, N prime, L, L prime, and ML, ML prime.
So double delta? It's actually.
It's a triple one, but I just wrote it that way.
Alright. Oh, right.
Yeah. So it was,
Yeah. Gotcha.
okay? So you can start calculating those things. I feel like I want to give another idea. It's completely unrelated to what we're doing right now. All right? But say I solve for an atom, right? Say I solve a problem for an atom, and I have H of an atom. All right, and that equals EK plus EP. And I know the energy, En goes like minus 13.6 eV over n squared. All right? And then I look at the expectation of this. I look at like n prime, L prime, ML prime, and then H atom, and then NL, ML. What do I get there?
It goes out.
Negative 14.6 EV times squared. Delta, contra delta.
I'm just going to leave it like that. We get it, right? All right. So if I'm someday interested in talking about a transition, like an electron making a transition from the n equals 2 state to the from the n equals 1 state to the n equals 2 state, right? Then that means this is something like a 2, and this is something like a 1. So does that ever happen?
Yes.
All right, yeah, the transition happens, but if I have the Hamiltonian of the atom, and it has this delta function of all these quantum numbers, doesn't that integral always go away?
Yeah.
Because they're not, they're orthogonal.
Because they're practically the same.
Okay, so that's right. So what we're going to find out later on is in order to connect things from different states and different levels, we're going to have to say there must be something more to the hydrogen atom. So there might be something like this. I'm going to call this H prime. All right? And when H prime acts on N, M, and ML, what it's going to have to do is it's going to have to, for example, operate on N and change this to an N plus an N prime. Because then if that changes it to an N prime, then it will be able to overlap with this and then give you a non-zero integral. All right, so later on when we talk, and this is more in quantum 2 when we talk about transitions, and I just wanted to mention it today, that there's going to be other things that we can add to the Hamiltonian. And remember, the Hamiltonian is an operator, so how can it change an N? Well, an operator takes derivatives of things, right? An operator multiplies things, all right? So it might act on this thing to change this side. So it might not even be eigen, right? So it wouldn't be an eigenvalue then because it operates on to change that. But a result of changing this side will now, when you compute the integral, give a non-zero integral and will allow that transition to happen. All right?
Somehow affecting the Hamiltonian will affect.
Yeah.
Does that connect to Feynman's pictures of?
Yeah, you need that in Feynman diagrams.
Yeah.
It's how you connect different states, ingoing and outgoing states. All right, and there has to be something in that connection that does something to one to make it so that the overlap integral, then they're called overlap integrals. And it has to do something to do it, to change that wave function so that the integral doesn't equal 0. I don't know if I would mention that, but I didn't. All right, but let's get back to the story. So that's the angular momentum. And that is angular momentum that is created how? What is that? Is that intrinsic angular momentum or is that angular momentum?
It's intrinsic.
It's not intrinsic angular momentum. Right? It's angular momentum of the electron. And where does it come from? Where does angular momentum of the electron come from?
Spin.
No, so that's intrinsic angular momentum. So where does the normal angular momentum come from?
There was orbital speed.
Well, okay, orbital momentum, yeah, not just its speed. All right, but it's r cross p. All right, so that angular momentum is truly angular momentum created from r cross p. All right?